In today's video, we're going to be talking about a new branch of mathematics called optimization. Well, guess where this branch comes from? This idea of optimization really is optimization. I'm just talking about finding minimums and maximums. And that's exactly what we talked about last week in our 2.1, 2.2, and 2.4 videos, is how to find minimums and maximums. So this stuff is all related, okay? Optimization is just kind of a more formal term we use for the mathematics behind this, or all the different mathematical problems that kind of boil down to the same process, okay? So for example, right, you might want to optimize the area of a garden plot. It means you want to find the maximum area. You might want to optimize your monthly payment, right, by minimizing it, by finding the minimum amount that you need to pay. You might want to optimize revenue by finding the maximum amount of money you can take in for a certain product. So all of this falls under this category of optimization. And what do we use in order to optimize? The derivative, right? We use the derivative to help me optimize. So let's look at an example. Let's say we're running a business, right? And I'm able to create a revenue equation for, sorry, let me just make sure I got this pulled up. We're able to create a revenue equation for a specific product. My revenue equation is 7x minus 3x squared. We're also able to find a cost equation for a specific product. X cubed minus 4x squared plus 1. And if you remember, with these equations, x represents the number of products produced. Okay. And this is... And just to keep in mind, in our specific example, this is in the thousands. Okay, so what if I asked you the question, or what if I gave you the task, right? If you're a professional, that's how it would work. And if in the workforce, your employer would come to you and say, okay, this is what I want you to do. I want you to optimize our profit based off of these equations. What is your employer asking you to do? Profit means the money you get to actually take home. So what would we want to do with that? We would want to maximize it. We want to find the maximum. Okay. Well, before we even get started, I do need my profit equation, right? So remember, profit is equal to revenue minus cost, right? The total amount you take in minus what you have to spend on that product. So let's go ahead and do that. Let's do revenue minus cost. I get 7x minus 3x squared minus x cubed minus 4x squared plus 1. And I end up getting negative x cubed plus x squared plus 7x minus 1. So there's my profit function. Okay, if I want to optimize, if I want to find the maximum, I need to find the critical points, right? I need to find where my profit is leveling out, switching from increasing to decreasing. So I need to find my critical points. How do I do that? Take the derivative, negative 3x squared plus 2x plus 7. And what am I going to do with that derivative? I'm going to set it equal to 0. Okay. So we see that again, right? Take the derivative, set it equal to 0. That's going to be part of this optimization process too. Okay, so keep getting used to it. Okay, I can't factor this, so if I want to solve this, I have to use quadratic formula. And it turns out I get 1/3 minus the square root of 22 over 3. And I get 1/3 plus the square root of 22 over 3. Interesting. So I get 2 possible points where I can find my maximum. But take a close look at those 2 points. There's actually one that I can automatically disqualify. Which one? This one. Why? Sorry, I should have put let me wait on putting the slash through it. Why can I disqualify it? This is going to end up being a negative number. and I don't want to produce negative values or negative products, right? I can't produce negative products. So negatives are not defined in this context. I'm only looking for positive values. So there's my positive value. This ends up being about 1.897. And once again, this is in thousands, so this means me producing 100. Sorry, in fact, we won't put it next to X, I'll just say this. So 1,897 products. Okay. What about this? What about 1,897 products? Well, doing this gives me a maximum. Now, I didn't actually test to see if it was a maximum, but you can test to see if there's a maximum by either using the first derivative test or the second derivative of this isn't complicated to find at all. I could find the second derivative and plug in 1,897 and see what I get. But because this is the only valid critical point, we can be pretty confident that this is going to maximize my profit. This is going to maximize my profit. Okay? So we are done. This, in fact, let me use the word optimize because that's the name of this section. This optimizes my profit. Okay. So you'll probably see an example like this on the homework, but so feel free to pause this now and you can try out a few problems, and then we'll keep going in just a little bit. Okay, let's take a look at another example. This one is more geometry. Let's optimize the area of a quadrilateral. Okay. Now, we're not going to get into trigonometry here, so let me go ahead and just say, in order to optimize area so quadrilateral, right, it's a four-sided shape. In order to optimize the area, we're going to want 90-degree angles. Okay. What does that mean? That means we're either working with a square or a rectangle. Okay. You might already be able to guess which one we end up with, but we're gonna actually prove it here. Okay. So let's say I want to optimize the area of a quadrilateral, and let me go ahead and add with a perimeter of 36. Okay, I actually need to put that in there because if I don't give you a perimeter, you can just then there is no. This gets into, right, if I don't give you a specific domain, then there is no absolute maximum because you could just end up going to infinity. You can have an infinite size quadrilateral because you're not limited by anything. So I do need to give you a perimeter. We call this a constraint. Otherwise, I wouldn't be able to solve this problem. So this is called a constraint because it limits my values. It gives you a limitation. Okay. So I want to optimize the area of a quadrilateral. Well, if I want to optimize area, I need an equation for area, right? Because once again, the whole process of this is we're going to take the derivative of a function and set it equal to 0 to find critical points. In order to do that, I need an equation. So I need an equation for area. If I'm taking the area of a quadrilateral, I'm doing length times width. Okay, length times width. Right? Because it could be a rectangle. We're keeping that option open. It could be a rectangle. So length times width. To help you out, right? Here's a picture, right? Length times width. And just a little reminder from your geometry days, a square counts as a rectangle. A square is a type of rectangle. So that's why, don't worry, this covers squares too. So there's my equation for the area of a quadrilateral. So now, like we said, okay, I'm going to want to take the derivative of this and set it equal to 0. But I run into a problem. This function is in terms of two variables. How do I take the derivative then? Which variable do I choose to take the derivative of? And then if I pick, like, okay, let's take the derivative in terms of width, what do I do with the length variable? Right? So I run into the problem that I have two different variables that I'm working with, two unknowns. I don't know the length and I don't know the width. How do I deal with this? How do I get around this? Well, like we said earlier, in order for you to solve this problem, you need a constraint. So this is where the constraint comes into play. What does this constraint tell me? My perimeter has to be 36. Well, I can write an equation for perimeter, right? My equation for perimeter is 2L, right? You got a length on bottom and a length on top, plus 2W. You have a width on the left and a width on the right. To get perimeter, you add all of your sides together. What does it need to equal? It needs to equal 36. So it turns out I have an equation for my constraint. But what do I do with this? Well, what I can do is I can solve for one of my variables. So if I subtract 2L onto both sides, then divide by 2, I get 36 divided by 2 is 18. 2L divided by 2 is just L. I get that the width has to be 18 minus the length. So the constraint lets me solve for one of my variables in terms of the other one. How does that help? Now I can go back to my area equation and replace width with what it is in terms of my length. Right? Do we see that? My width is equal to 18 minus L, so I can replace W with 18 minus L. And that gives me the area is equal to 18L minus L squared. How is that helpful? Well, now I have my area equation just in terms of one variable. It's just in terms of my length. So, can I find my derivative now? Absolutely. So what's my derivative of my area function? Derivative of 18L is just 18. Minus derivative of L squared is just 2L. I know it's not X, but we still do the derivatives the same exact way. Now that I have my derivative, what am I going to do? I'm going to set this equal to 0. Set it equal to 0 and solve. I get 18 equals 2L. Divide by 2 and I get L is equal to 9. So, in order to optimize the area of this quadrilateral that has with the perimeter of 36, I want my length to be 9. Okay. Well, what does that mean my width is going to be? Well, to figure out my width, I can just come right back up to this equation, and my width is just equal to 18 minus what my length was. My length is 9, so I can plug in 9, and I get 18 minus 9 is also 9. So that means my width also needs to equal 9. And sure enough, it turns out to optimize the area of this quadrilateral, what shape does it need to be? It needs to be a square. Square will optimize the area of a quadrilateral. Okay. Pretty cool. So a lot of the problems that you're going to see on the homework are similar to this one, where if you try and take the derivative right from the very start, you're going to have multiple variables that you're dealing with. And in order to overcome that, you need to use your constraints to get it all in terms of one variable. Okay. Go ahead and pause the video. You can try a few more problems, and then I'll go through a more complicated one. So for a more complicated example, I chose number 7 from your homework. Okay, so this is number 7. You guys are welcome to pull that up and take a look at it as we go through this. Because I feel like this is a really cool example of, okay, what am I optimizing? What are my constraints? So this is about a university trying to determine what price to charge for tickets for a football game in order to optimize revenue. So I'm optimizing my revenue. That means I want to find a maximum. I want to maximize my revenue. Okay. Well, so with that in mind, the first thing I might think to do is, well, that means I need a revenue equation, right? I need to have an equation for revenue that I can then take the derivative of and set equal to 0. So, but in order to write this equation, we need to understand where this revenue is coming from. If you're at a football game, your two main sources of revenue is, first of all, ticket sales. Hopefully that makes sense. But your other main form of revenue is concessions. People buying concessions. So this doesn't look like an equation because I'm just using words right now. So we need to actually get numbers into here. So let's think about and you can use the problem to kind of help you figure this out. But let's think about, how do I actually calculate your revenue from ticket sales? How do I calculate this first section? Well, you earn money, ticket sales wise, you earn money for each ticket sold. Theoretically, how many tickets were sold? However many people attended the game. So your attendance is a major factor on how much money you make in ticket sales. Okay, so let's do capital A, or no, lowercase a for attendance. So A is equal to attendance. How many people showed up to the game? But what else does it depend on? Right? If you give away seats for free, you're not going to make any money in ticket sales, right? It also depends on what price you charge for your tickets. In fact, if you look at the problem, that's what they're asking you to figure out. What price should you charge in order to maximize revenue? So this represents so your ticket sales also depends on the price of the ticket. And so to get those ticket sales, it's just however many people attended multiplied by the price of a ticket, right? Because if your ticket is $10 per person, you're going to make $10 for every person that attended. 10 times your attendance. Okay? Attendance times price. Okay? This is actually going to be a common theme as we get into more of these, like a lot of these business applications. Revenue, you can commonly just find as price times quantity. What price are you setting? How many are you able to sell? Price times quantity. Okay, and in our case, quantity is the attendance. But our revenue has this extra section of concessions. How do I calculate concessions? Well, if you read the problem closely, it says every person at the game spends an average of, and then they give you a certain amount of money on concessions. Notice, we're not worried about profit. We don't have to try and compensate for how much we're spending for these concessions. We're just worried about revenue. Okay. So in my problem, each person was spending an average of $6 at concessions. So that means my concessions is $6 per person. Well, what's per person? The attendance. This is 6 times the attendance. Okay. So pretty similar, right? It's $6 per person at concessions, and ticket sales, it's the price of the ticket per person. The difference is I don't know what I'm charging for my tickets yet. I do know what I'm raking in for concessions, but I don't know the price that I'm setting for my tickets. So what does this leave me with? This leaves me with an equation that I can optimize that's in terms of 2 different variables. So how do I get this in terms of only one variable? I need a constraint. So if we read closely, there's one more piece of information that there's a couple of pieces of information that I haven't actually used yet. First of all, they give you this information. At a price of, and in my case, it's $18 per ticket. So if I set the price at $18, it corresponds to 40,000 people attending. Okay? So if I set the price at $18 per ticket, then the average attendance is 40,000 people. What does this begin to tell me? This begins to tell me that there's some sort of relationship between price and attendance. We're going to talk about this later. It's called a demand curve. The higher you set the price, the lower the demand. The lower you set the price, the higher the demand. So there's this relationship between what I set the price and how many people attend. And so then it tells me something else. It tells me that every decrease of $3 adds 10,000 to the attendance. So what does that tell me? An easiest way to make sense of it is I could, an easy way to make sense of this is what happens if I just lower the price to $15? According to this, only 30,000. Oh, sorry. No, it adds 10,000 to attendance. My bad. An additional 10,000 would show up. So I would have 50,000 attendance. Okay. If I kept going, if I went down to $12, an additional, I would have 60,000 people attend because 10,000 more people would attend. Well, what does that sound like? That sounds like a linear relationship, right? Every decrease of $3 add 10,000 to attendance. That looks like a slope. Up 3 over 10,000, or over 3 up 10,000. That's what. So this right here is a linear relationship. If it's a linear relationship, I can write an equation. Okay, so let's see if I can write an equation for this. First of all, let's see. Let's have P be my X and A equal my Y. So if I do change in Y over change in X, I get 10,000 over -3, right? I add 10,000 when I decrease my price by 3. 10,000 over -3. So there's my slope. Okay. So then to write my linear equation, I can use point slope form, right? Y minus, what did I set my Y as? My attendance. Okay, so in fact, I should actually replace Y with A. A minus my attendance, 40,000, right? This is point slope form, so I'm just using one of my points. That means I don't have to find the y-intercept. I can just use one of my points. So A minus 40,000 equals my slope, 10,000 over -3 times X. Well, in my case, X is the price, so P minus 18. 18 is my corresponding price to having 40,000 people attend. Okay, so with that, I can then solve for A. I can do some simplifying and solve for A, and I get 10,000 over -3 times P plus 120,000. By the way, if you're curious, what that 120,000 is how many people would attend if I set my price to 0, right? It's my y-intercept. If I gave away my tickets for free, we could expect 120,000 people to show up. Well, awesome. So what this does is that gives me my attendance equation all in terms of price. And so now so this was my constraint. This represented my constraint because it was the additional information that I needed to solve this. So this was my constraint. I got an equation that was in terms of my other variable. And what that allows me to do is come over here and rewrite this equation completely in terms of my P variable. Anytime I see an A, I can replace it with this equation. Times P plus 6 times my attendance, which once again, my attendance depended on the price using this function. Okay, very nice. So I know that's a lot, but the big idea is that this is now all in terms of one variable. So let me do some simplifying. I'm gonna go ahead and distribute the P, right, I'll go ahead and distribute the P to both terms. I'll go ahead and distribute the 6 to both terms. And let's see what we end up with. Okay, so this is just me simplifying this ugliness. I get negative 10,000 over 3. I just moved the negative out of the denominator. P squared plus 100,000 P plus 720,000. Okay, very nice. If in case you're curious, what does this 720,000 mean? This now represents the revenue I would get if I gave away my tickets for free. You might be wondering why you're still getting revenue. Remember, concessions. So this would be the amount I would earn on concessions if I gave away the tickets for free. Anyway, but now look at that. That's just a simple quadratic function. I can take the derivative of that easy. So now that I have my revenue equation all in terms of one variable, I can now maximize. I can optimize. I can find the minimums and maximums by taking the derivative, setting equal to 0 to find the critical points. So let me take the derivative. I get negative 20,000, right? Because I have to multiply it by 2 using the power rule. Negative 20,000 over 3p plus 100,000. And then I'll set it equal to 0. Solve for p. Set it equal to 0. Solve for p, and you end up getting p equals 15. Very nice. So notice there's only one critical point. So I can go ahead and assume that this is what's going to maximize my profit. This is what's going to maximize my revenue because it's the only critical point. 15 what? Once again, P represents price. So this is setting my ticket to $15 a ticket. Very nice. Okay. And then in case I was curious, in fact, I think the problem might ask you this is if I set it to this price, how many people will attend? Well, to do that, all I need to do is just plug 15 into this problem, and I get, in my case, I get 70,000. So 70,000 people attend if I charge $15 a ticket. No, that's not right. Oh, I think they've got it. I might be looking at a different problem. Yeah, I mixed up my numbers here, but regardless, the process is the same. Okay. Awesome. So let me just double check because I think I may have 720. Yep, that looks good. Okay. So, sorry, my attendance is actually only 50,000. Yes, my attendance is only 50,000. Perfect. Okay. So, with that in mind, then if I really wanted to, I could plug this price back into my revenue equation and figure out what my total revenue would be. But that's the process. So if we were to kind of finalize this process of what we actually did. First, so actually this is for, and let me just, sorry, before I get going, this is for optimization. The optimization process. First, write the equation that needs to be optimized. It may or may not be in terms of one variable. It might be in terms of 3 variables, 2, 3 variables, whatever's unknown, right? So to deal with that, find your constraints. And use them to rewrite your equation and only one variable. Right? So in our example, right, my initial function was in terms of two different variables, attendance and price, but then I used my constraint to get this equation, which allowed me to rewrite my revenue equation in terms of only one variable, price. Step 3, find the critical points. And this is the step that's the same as what we did in 2.1 and 2.2. Find the critical points by finding the derivative and setting it equal to 0. Okay, very nice. Feel free to rewatch or whatever you need to do to make sense of all the other problems in this on your homework. Feel free to reach out to me if you have any questions. But good luck.